Hey guys, Mr. Ray's here to help you out on the first part of chapter 4. So we got 4.1, and what we're going to be looking at are things known as antiderivatives, or also known as indefinite integration. So we're going to write the general solution for definite equations and use indefinite integrals notations for antiderivatives. Another goal is to use basic integration rules to find the antiderivatives. And then towards the end of this, we're going to try to find a particular solution for a differential equation. So a function capital F is an antiderivative of f on the interval I, such that capital F prime of x is equal to f of x for all x and I. So let's kind of go through an example and talk about what that means. Is if we want to go through and find, okay, if we had x cubed, what would capital F be? So if we had to go backwards to figure out, okay, what derivative equals 3x squared? Well, think about it. Well, capital X would have to be x cubed, right? Because if we take the derivative of x cubed, that would be 3x squared. And that is the same thing as regular f of x. Okay. But is that the case? Is that it? Is that just it? Is that what capital F has to be? Let's double check a couple things. What if we said f sub 2 or f prime sub 2 is x cubed minus 5. Well, what's the derivative of that? Well, that would be x cubed would be 3x squared. The minus 5 would go away. What about this one here? What's the derivative of that one? Well, if we take the derivative of the x cubed, that's 3x squared. The plus 97, that goes away. So here's the thing that we have to always watch out for any derivative or any antiderivative is then when we go backwards here is, if we take the integral of an equation, we always have this common number at the end, this constant number at the end that can be included. So whenever we take the antiderivative, we're going to have to include this plus c, meaning that the antiderivative equation is this part of the problem plus some constant number that could be added on the end. It could be a 0 added on the end. It could be a 1. It could be a negative 12. It's just some constant number. So here's a big thing. Whenever we do these integrals here, the integral of f of x is capital F of x plus c. You have to remember the plus c. I can't tell you how many times I had college professors that just freaked out if you forgot the plus c. All right. So let's go through, and what we're going to do is try to use some of this notation here. So we know, like, okay, if I wanted to find the derivative, if I have f of x, the derivative is f prime of x. Or we could say, like, what we did technically was like d dx. Now, if we ever want to go backwards, we're going to use this like nice little squiggle sign. This is called an integral sign or integrand. So what we have to do is do a couple special things to show that we do that. One thing is that we're going to use this little integral symbol to represent we're taking the antiderivative. But at the end of the problem, we're going to have to put this dx. For you guys, that's not going to mean too much. Sometimes we could do a dx or dy. And if you remember, like when we took the derivative with respect to x or the derivative with respect to y, we had to do those special little things. Technically, those rules still apply if we take the antiderivative. But in this class, since we're just kind of dipping our toes into it, that dx is pretty much always going to be dx until like the very, very last section that we cover. All right, so don't worry too much about it. So here's some basic rules about integration. If I want to take the integral of the derivative of f, so let's try to think about what this means here. If I take f prime of x, okay, if we remember the derivative of the antiderivative is f of x dx, and then the integral of that would be f of x plus c. So if we look here, basically what I want to show you guys is that for the most part, derivatives and antiderivatives cancel each other out right here, because right here we have the antiderivative and that little apostrophe means we're taking the derivative of it, but not completely. Because this problem say, hey, take the derivative of the integral. So if we leave the derivative part alone, we do the inside part of the parentheses, the integral of f of x plus c is capital F of x plus c. If we take the derivative of that, the derivative of capital F of x is just regular f of x. And the derivative of the plus c goes away. So they don't technically always cancel each out, but for the most part, other than this constant here, derivatives and integrals cancel each other out. So let's talk about some basic rules here to know. We know some basic derivative rules, like the derivative of any constant is 0. Well, the integral of that, the integral of any 0 would have to be some constant. We got the derivative of some number times x, we'd get some number. The integral of just some number would be some number times x plus that constant. So we're going to kind of use these rules throughout the way. Remember, we can just always pull some things out in front, and if we're taking things and separate them. Here's the biggest one here. The derivative was of some x to some power. Remember, if I had x to the 5th, we would get 5x to the 4th. Okay, that would go to 5x to the 4th when we took the derivative. Now to go backwards here, the integral of some number to the power. So if we had x to the 5th and we're going to integrate that, that would end up being x to the n plus 1. So this would be x to the 6th power divided by that number, 6. Which would make sense here, because if I took the derivative of x to the 6th over 6, we'd get 6x to the 5th over 6. That would just be x to the 5th. So we're going to use our derivatives to help us go through and double check things out. Okay, so those rules also apply with other things. And so my biggest thing is, like, if you ever have any trig functions or anything like that, just go back and kind of double check those things here. We know sine goes to cosine, so integral, cosine goes to sine. Switch it around, sine goes to negative cosine on the integral. So other ones that you might see there, like secant squared goes to tangent. Anything else really complicated, look back at this resource. I will let you guys use this on anything. Okay, so let's do some basic integrals here until we feel somewhat confident with this, and we'll do this first example here. So what's the integral of 3 to the x power? So what we're going to do is 3, we're going to bump it up a degree and divide by that number. What we're going to do is see if that reduces. If it doesn't, no, that's pretty much it. We'll put a plus c. Okay, now we can use our same tricks here. So really, we're going to do the integral of x to 1/2 power dx. So we're going to take that x, bump it up a power, 3/2, and divide by that. Now we're going to try to clean that up before we put our plus c. So if we're dividing by 3/2, that's the same thing as multiplying by 2/3. So this is 2/3 x to the 3/2 power plus c. All right. So you can see rewriting, integrating, and then simplifying is typically the 3 steps that you do here. So in this problem, 1 over 5x squared, we might want to change this to the integral of 1 over, if we actually square that, that's 25x squared dx. Now even that's a little complicated. We got something divided. We might want to change that to the integral of 1/25 x to the negative 2nd power. So we rewrote this here. Now we can do the integral. All right, so we got 1 over 25. We're going to bump that up a power. So this would be x to the negative 1 power. We divide by that number. Okay, so let's clean this up. If I divide this by -1, this would be -1 over 25. And the x to the negative 1st power would just be on the bottom here. So the integral would be -1 over 25x plus c. Okay, this one's a little bit easier. Now, if we just have 2 things separately, we take the integral of one thing, take the integral of the other thing. No need to rewrite the x here, so we can just jump right into the integral. The integral of x would be x squared over 2. The integral of 7 would be 7x. I say that looks pretty good here. Nothing to write, so we'll just put a plus c. All right, let's keep it going. 5x to the 5th plus 1. Okay, we can do those individually. X to the 5th becomes x to the 6th over 6. 1 becomes x. Technically 1x over 1, but x. And then plus c. Okay. Hopefully not doing too bad here. All right, let's crank it up a little bit here before we start, doing anything else. Okay, so if we have this would be quotient rule, but remember we can rewrite it. Technically, we're dividing everything by x to the 1/2 power. So we can take away an x to the 1/2 power from each one of those. X to the 1st minus 1/2 would be x to the 1/2. And then 6 divided by that would be 6x to the negative 1/2. So now that these are easier powers to integrate, we'll just integrate them separately. So x to the 1/2 would be x to the 3/2 over 3/2 plus 6. If we bump that negative 1/2 up 1, that would be to the positive 1/2 divided by 1/2. Okay, so let's clean that up a little bit here. Remember, if we divide by 3/2, that's the same thing as 2/3 x to the 3/2 power. And then plus, okay, if we divide by 1/2, dividing by 1/2 is the same thing as multiplying by 2. And so that would be 12x to the 1/2 power. And then we can do plus c. Now, typically with integrals, there's not too much that we're going to be doing with them in this classroom. It's not like we're going to be setting them equal to 0 or anything like that. So it's kind of okay to leave them in weird powers. Derivatives, you can find more critical things. Integrals, we will do work with integrals, but we're not going to be setting them equal to 0 as much as what we did before. Okay, well, what if we have a product, two things multiplied together? Well, what we could do is actually just FOIL this out here, make our life easier, see what that equals. All right, so x times 3x is 3x squared. Let's see, x times -2 would be a -2x, and then we have a plus 3x in the middle, so that'd be just a plus 1x, right? A -2 plus 3 would be plus 1. And then 1 times -2 is -2. So all we did was just rewrote the equation. We'll integrate it now. Okay, so 3x to, we'll bump that up a power, divide by that. Okay, that kind of works out real nice. X to the first bumps up a power to 2, divide by that, minus 2x. Okay, we could clean this up now. So 3x cubed divided by 3 is just x cubed plus x squared over 2. If you want to change that to 1/2 x squared, you can. Minus 2x. All looks good now. We'll put our plus c to kind of finish the problem. Okay. Next, we got trig functions here. What do they do? Okay, we got 5 cosine. All right, so nothing here to rewrite here. We just have to think kind of backwards here. We know that in a derivative, sine went to cosine. So if we go backwards, cosine must go to sine. All right, next, cosine went to negative sine. So this positive sign must have come from a negative or cosine of x, right? Because the derivative of cosine is negative sine. A -4 turns out to be a +4. All right, plus c. So not too bad. You just got to maybe take your second, make sure you're doing this right. All right, last one here. Okay, what do we do here? Well, we got a d theta, so that means everything is going to be theta. So if this was x or 1, we'd go to x, but in this case theta. So we got a theta, and then minus. What the heck does cosine times cotangent? I have no idea. That kind of scares me. So we're going to go back up our list here. Do we see a cosine times cotangent or cosecant times cotangent? Oh yeah, there we go. Cosecant times cotangent goes to a negative cosecant. So let's see, we already said that this would be a theta minus, and this would be a negative cosecant theta. And all we got to do is just clean it up. A minus and negative becomes a plus a positive cosecant. And once we got that clean and nice, we'll put our plus c to finish. Okay, so that's all we're going to do for the first part today, guys, is just getting used to taking antiderivatives. We'll do some more complicated ones tomorrow, but just kind of warming up today with the first part. All right, guys, so that's it. I will see you next time. Have a good one.